Going live on Facebook. Final connection is being made. It is 1800 on the West Coast. And we are now live.
Okay, shall we kick it off?
We shall. So everyone, thank you for joining us this evening. My name is Josh Gilliland. It's always a pleasure to have these great webinars where we can help local units have program activities. I want to turn it over to Bruce Johnson now, who's going to introduce our speaker. And thank you all for who've tuned in. If you have any questions, please use the Q&A function.
Okay, thanks very much, Josh. Good evening, everyone, and welcome to the second Coast Guard Tech Talks workshop for 2021. These workshops are jointly sponsored by the U.S. Coast Guard, the Coast Guard Auxiliary, and the Boy Scouts of America's Sea Scout program. My name is Bruce Johnson, and I serve as Chief of the Coast Guard Auxiliary's Youth Programs. Our co-host is Josh Gilliland, Chair of the National Sea Scout Communication and Marketing Team. Josh will be coordinating your questions in the third part of this program. Coast Guard Tech Talks are held monthly on the fourth Tuesday of the month at 2100 Eastern, 2000 Central, 1900 Mountain, and 1800 Pacific Time. Each program focuses on a single science, technology, engineering, mathematics, or STEM topic. These topics are chosen to support the Sea Scout Advancement Program. Next month's Tech Talks workshop will be on tides and current. Tonight's topic is Global Positioning System, or GPS. Our presenter is Coast Guard Lieutenant Josh Allman. Lieutenant Allman is an aircraft commander of an MH-65 Delta Dolphin helicopter at Air Station Atlantic City. He earned his bachelor's degree in aeronautical and astronautical engineering from The Ohio State University, during which time he enlisted in the Coast Guard Reserves and drilled at Coast Guard Station Cleveland Harbor. Subsequently, he worked for Augusta Westland, now Leonardo Helicopters, as an engineer on the AW119 and AW139 helicopters and the AW609 tilt rotor prototype. In addition to his current role as Coast Guard search and rescue pilot, he works in the Aviation Engineering Department at Air Station Atlantic City, where he enjoys conducting maintenance test flights and designing test programs for new equipment on the MH-65. One last thing, we've muted your microphones to make it easier for everyone to hear. If you have questions, please ask them in the Q&A box. Josh will be monitoring the chat and will be sure to leave time to answer your questions. So let's please welcome Lieutenant Allman.
Hi, thank you very much, Bruce, for the great introduction. Really, everything I was going to say, you pretty much just covered there. So I'll just add on a couple of personal notes. I was mostly raised in Ohio and of course went to Ohio State, so huge Buckeye football fan still. Since moving to the unit here in Atlantic City, New Jersey, me and my wife are actually living in Philadelphia, Pennsylvania. Usually that means that we get to enjoy the museums and all the great things that this historic city has to offer. But obviously this past year has been a little bit different. On another personal note, Lieutenant John DeCastra is how I came to know about this program. And we actually went to flight school together about 3 years ago down in Florida. So we got to know each other quite well. And he invited me to be a part of this. And I'm very excited to do that. One caveat, I am by no means a GPS expert. I do have that engineering background, so I was able to piece together a lot of research, and I think I've got a pretty good understanding of everything that's going on. Everything that you're about to see, we'll cover the resources, but I've got a couple good references that you guys can dive into further. And during the Q&A session, I hope to answer as many questions as I can. For anything that I can't answer, we will stick with references, and if I can, I'll get back to anybody who has lingering questions that I'm not able to get to. With that, I'm going to go ahead and get my screen shared, and we will begin. All right. So just a quick outline. First, we're going to talk a little bit about just latitude and longitude and what that means for referencing position on the Earth. From there, we're going to go into the actual lat-long format, meaning the numbers and what they mean and how they can change different formats. And that's just going to be a brief overview. I'm sure some of you have already dove into that with other topics that you've studied. But for anybody who hasn't, we'll just try to give a little bit of background before we get into the real meat and potatoes, which is the satellite navigation system itself and how it operates. And then I just have a very simple, straightforward, practical exercise that's geared towards really the end user, which is how the system is designed. The main two references I want to point everyone towards for after this, if you have things that you want to research for yourself. The first one with the Smithsonian Institute with time and navigation, and then the third one being gps.gov. Those are two excellent resources that I learned a lot about global navigation. All right, so kicking it off, so latitude and longitude. In its most basic sense, it is a grid system that's wrapped around the surface of the Earth. It essentially dates back to how ships navigated and circumnavigated the globe. And essentially what we have is, starting with latitude, we are going to start at the equator, which we're going to call 0 degrees, and go north and south to 90 degrees respectively. And basically each of those degree circles are concentric circles, and the significance of the concentric circle is that all of the distances going from north to south actually remain the same. And you can see on the right over here how those lines are all parallel, which means that they never get closer, and you're always going to maintain that same distance. So specifically, this point here is going to be referencing 40 degrees north, which we'll get to as well. And in fact, I'm going to change to the laser pointer just so that my cursor is a little more obvious. All right, so that's north to south. That's what we call latitude. When we talk about longitude, what we're talking about is directions going east and west. Now, we don't have as perfectly defined of a starting point as we do as the equator. So instead, what they came up with years ago was starting at what we call now the prime meridian. And the prime meridian is the point that runs north and south through the point of Greenwich, England, which is essentially where this method of navigation was first started. So each of those lines is going to run from north to south. So north here and south here, of course. And the main difference, as you can see with this diagram, is that the lines actually converge at the north and south poles and are widest at the equator. So as we're traveling east and west, those distances don't necessarily remain the same. And while that's not going to make a huge difference in how we actually use our GPS devices, it is notable because when we are comparing things to a chart, or if we're trying to transcribe a GPS position to an actual nautical chart or even an aviation chart, that is going to make a bit of a difference in how you actually measure to get to that point. So in this example specifically, again, referencing this point, we would call the longitude the 30 degrees west. So just to point out, latitude would lead longitude. All right, so just an example to kind of bring it home, and then the breaking it down between the degrees. So degrees obviously are very wide margins. To get to a more finite point, we're going to discuss minutes and seconds. And really, if you think of a clock, a minute is just going to be, or sorry, 60 minutes would be 1 degree. So we're breaking up a degree into smaller intervals called minutes, and continuing down, then we have seconds. So again, 60 seconds in a minute. And really it's very similar to thinking about a breaking down time as if you're looking at a clock. So for the example, basically, I wanted to point out first, we're going to look at latitude. So going north along this line would mark 10 minutes. And then if we skip up to the top of this grid, this would mark 30 minutes. And then latitude going west is going to go 10 minutes, and then skipping ahead 30 minutes. So of course, I'm going to reference my air station at the airport for Atlantic City. And if we wanted to plot the latitude and longitude of 39 degrees, 27 minutes, and 27 seconds, we would find 39 degrees on our chart. We would then go up to 27 minutes, which is going to be right about here. And then count an additional 27 seconds, which since we don't have seconds marked on this chart, really we're just going to go about halfway between the 2 minutes. And then going west, we of course have 074 degrees. So there's 074 degrees. Then we're going to go west to about 34 minutes, which is going to be about here. And again, we'll go a little bit further for the seconds, and we'll just approximate it about halfway in between. So hopefully that kind of covers what we're talking about. If anybody has questions about how I explain that, please bring it up and we will address that. All right, so getting into the format a little bit, you're going to see latitude and longitude displayed in a few different ways. The main difference are basically you can break it into 3 categories. You can discuss the position in terms of degrees, minutes, and seconds, which is what we just described. You can instead essentially exclude the seconds and use what's called decimal minutes. And really what we're talking about is a fraction of a minute. So instead of counting to 60, we're counting to 100 essentially. And then if we wanted to further break it down, instead of minutes, we could use decimal degrees. So all 3 of these positions are actually the exact same position. And to prove it, I'm showing my math here because I had some good math teachers and they really drilled it into me that I needed to show my work. So if we took 27 seconds and then just divided it by 60, that would be 0.45. So in other words, it'd be 45 hundredths of a minute. If we wanted to go a little bit further to get to decimal degrees, we would then take that, sorry, let me back up. So 0.45, we would then tack that on to the end of 27 minutes. So 27 minutes and 45 hundredths. And then if we wanted to go a little bit further, we could take that 27.45 divided by 60, which leaves us that 0.4575. And so that's saying we are actually at 39 degrees and then 0.4575 of that interval degrees. So roughly halfway in between 39 and 40, in other words. And then similarly, we can do the same thing, but going in the opposite direction. This time I used the latitude just to prove it works for both. So what we would do is if we're starting here with decimal degrees, we could take the remainder of 0.5772, multiply it by 60 instead of dividing. We would get 34 minutes decimal 63, so 34.63 minutes. And then if we wanted to turn that into seconds, we would take the remainder of decimal 63, multiply by 60, and we have our 38 seconds. So you can go either way, up and down, and all of these mean the exact same thing. Sometimes you're going to be using a GPS device and it's not going to look like any of those. Really, they're just trying to trick you a little bit. So they are going to be one of those 3 formats, but they may be omitting punctuation or changing the punctuation. So this is actually going to be a pretty common format, and we're going to run into this later actually. So what you're reading is 39 degrees, 27 minutes, 27 seconds north, and then 074 degrees, 34 minutes, 38 seconds west, which is of course the same position we were talking about earlier. Similarly, you can omit north and west and instead just use a positive or a minus. In the case of latitude, north is going to be the positive and a negative will be south. And for east and west, the east is going to be positive while the west is negative. So again, this is the exact same airport position, Atlantic City, and you would read this, 39 degrees, 27.45 minutes north, 74 degrees, 34 minutes, 63 west. All right, I think we've beaten that up. Just my example really quick to show. All right, so this is the same 2 points. We're just going from Air Station Atlantic City to actually my apartment in Philadelphia. So you can see it's the same points, it's the same trajectory, it's the same route, but this is in one format. And then to get it to this other application, we need to convert it to a slightly different format. So we're going from the degrees, minutes, seconds to the degrees, decimal minutes. And now we will continue. All right. So in a broad overview, very broad strokes, global positioning system was actually first developed by the United States Air Force, and it was then implemented and continues to be maintained by the Air Force. The project was started in 1973. That then turned into launches continuing essentially through the 80s to get it to full operation in 1993. Before 1993, we still had very good partial operation, pretty much exclusively for military use at that point. But then as they were able to add more and more satellites, we were able to get better coverage throughout the world and then also refine the accuracy of the solution. At this point, basically military and civilian use are practically identical. We'll actually get to that a little bit later, but know for now that it's the exact same constellation of satellites that's used by the military as is used by the civilian market. So how does it work? So we'll get into each of these steps in a little bit more detail, but just to give a quick overview of the things that we're going to talk about essentially. So this is from the Time and Space website with the Smithsonian. I really like how they break a lot of this down to a pretty digestible pace. They have it broken up into essentially 4 steps. So the first and second step, really you can just think of, we have a lot of ground installations, they're communicating with the satellite, and that communication largely is determining exactly where each satellite is in space and at what time it is at each position as it orbits. And we'll get into kind of that orbital trajectory in a later slide. The second step is essentially each satellite is, or really, I guess the third step, according to how the Smithsonian diagram has it laid out. The third step is each satellite is then going to take that information. So the position and the time are the 2 biggest pieces, and it's going to be broadcasting that signal of where the satellite is in space, as well as the time of when it is sending that position signal out. Last step is ultimately our GPS receiver. So that receiver is going to be getting the signals from various satellites, and it's going to essentially do a pseudo range, which we'll get into. You can think of it in the crime shows where they talk about triangulation of cell phone towers. Similar concept. Actually, it's incorrect verbiage, but neither here nor there. Essentially, it's using multiple different locations, multiple satellites, and figuring out where it is relative to those satellites. All right, so getting a little bit deeper into each piece of that. So the ground control portion, basically everything is maintained out of Schriever Air Force Base in Colorado Springs. They have continuous monitoring, and they have a whole host of functions, and we're really only going to skim the surface as far as what they do. The main portion, like we already talked about, is they are essentially figuring out, or they're maintaining the computers that figure out exactly where each satellite is as it orbits the Earth. And the satellites themselves are going to be on predetermined paths. So they essentially know where they should be at any given moment, but then they're going to use various radar and antenna to ensure that they actually are at that location. And if they're off by a little bit, that will play an important part in the end calculation. So they can either send essentially corrections for the calculation, or they can even control the satellite and get it perfectly back into orbit if they need to make those small adjustments. One of the main functions, or one of the main pieces, I guess, of the equation, like we've already briefly alluded to, is the timestamp, so to speak. And so in order to use an accurate timestamp, we need a super accurate clock. So we're using the US Naval Observatory Master Clock, which is actually in Washington, D.C., or we can use the alternate clock, which is, I believe, actually at Schriever itself. We also have a backup location. We always have to have redundancy in the system. So if they needed to shift operations over to Vandenberg Air Force Base, they can do so. And then, of course, you can see from the diagram that there are several monitoring stations, tracking stations, antenna stations. All of those are playing a part in tracking the satellites and where they go. Something I found interesting is that when the system was first started, they actually only had about 6 of the ground tracking stations. And you can see by the yellow triangles, they're kind of clustered in the northwestern hemisphere right around the US, which makes sense because we want to obviously know where we're at within the US. But for military applications, we need to know where military assets are all over the world. So the accuracy as you moved around to the other side of the globe essentially wasn't quite as accurate. So I believe it was either late 90s or early 2000s, the National Geospatial Agency ended up standing up 10 of its own tracking stations. And with the increased number of ground tracking, we're able to greatly increase the accuracy of the end result, just because there are more locations tracking more satellites, and that refines the solution by providing for more calculations. And I think that is, yep, that's about all I have for there. All right, so getting into the satellites themselves a little bit. We need a minimum of 24 satellites. We have essentially 6 orbits or orbital planes, and there are 4 satellites in each of those planes. By having that minimum number, we can ensure that a GPS solution can be calculated anywhere on the globe. If you start falling short of that, you start getting into essentially blackout areas where you may not have enough satellites to actually provide a solution for that zone. And that's simply because you wouldn't have enough satellites in view to provide a redundant solution. Of course, going back to redundancy, we don't settle for just the minimum number. We're going to go above and beyond. So typically you're going to see at least 32 operable satellites in orbit at any one time. This number actually fluctuates a little bit. Typically it tends to be a little bit higher than 32. And what's going on is each satellite is going to have periodic maintenance, or it might even have a malfunction, or the Air Force and NASA may be replacing satellites periodically because they do eventually run out of its service life, which tends to be about 7 years. Well, 7 years is the plan. They actually do tend to go much longer than 7 years, but they will schedule when they bring them out of rotation and send a new satellite into space. The cool thing about using 6s in math is by using at least 30 satellites, we now have at least 1 extra satellite in each orbital plane. And of course, the more we have, the better. And we're just increasing the amount of coverage that any one section of the Earth's surface actually sees in terms of having a satellite in its view. The more we have, the better it is. That's the end topic there. For the actual orbits, so this is something that I get a little bit more excited about just because it was more part of my background with aeronautical engineering. But we could dive into this for days. I'll talk only about a couple of the points. So in order to provide the solution or to calculate the solution, we need to have a relatively constant altitude of the satellite in respect to the Earth. For our system, that's about 11,000 miles. What's difficult about this is per what Kepler found when he was studying planetary motion, orbits really are ellipses, and even the most perfect circle is still an elliptic orbit. It just has the smallest variation that you can possibly manage. We do this in a couple different ways, and it's under the umbrella of what we would call a geosynchronous orbit. The main way that you get a relatively constant altitude is by equalizing, essentially solving the solution so that your speed at which the satellite is traveling is fast enough that it doesn't want to sink back into the Earth and then slingshot into the elliptical orbit. And then, of course, neither too fast nor too slow. But if you get that speed just right, just like, I guess the warm porridge, you can get nearly a perfect circle. And so that's what we're shooting for. Further, you can break it down into a geostationary orbit, which means that as the satellite orbits the Earth, it's actually so far from the Earth that it is essentially staying above the same relative position on the Earth's surface. But in order to do that, you have to have a pretty large altitude. It's a very far orbit, or much higher than what most of our satellites and even the International Space Station, much higher than where they tend to orbit. So it's very good for certain things, but then it can create some obstacles just because there is that much more distance to cover when you're relaying signals back and forth. Instead, what we do is our GPS satellites actually complete 2 orbits in a day. So they are on the same line of trajectory as they cross the Earth's surface, but they're doing it a little bit faster, or about twice as fast as what the Earth is rotating. So we have a exact trajectory that we know, and therefore we can make calculations through that prediction. But we're able to do we're able to conduct the orbit at a much closer altitude than the geosynchronous one. So we're able to essentially provide the accurate calculation with that nearly circular orbit, but without the increased distance. The satellites themselves, they've gone through actually, I think, about 3 iterations as far as the actual design and components, but this is essentially the main points. So you have approximately 1 ton satellite, so roughly 2,000 pounds, and really you can think of it as like a small vehicle, which in my mind, I think that's pretty large when you think about satellites. Maybe not, I don't know. I always think of satellites as something maybe a bit smaller. Maybe that's because I always think of Sputnik, which is closer to the size of a basketball. But in our case, these are actually pretty big pieces of machinery. Pardon me. So on board those satellites, we have thrusters and fuel. As mentioned previously, sometimes we may need to alter the orbital trajectory that it's on. And that's all that those thrusters are doing, are just maintaining that precise orbit. And then they are also keeping the satellite oriented so that the antennas are all pointing directly towards the Earth. Because if these antennas are pointed in the opposite way, we're not really doing ourselves much good by getting in terms of getting the signals that we're trying to get. And then, of course, we've got solar panels to power them, and the solar panels only work if they are facing the sun. So as the satellite is orbiting the Earth, it is making all of these corrections both to the body of the satellite as well as to the solar panels. So then we get to the atomic clocks. Really, this is kind of the essence of how we're able to create an accurate solution. This is another area that I get just a little bit nerdy. So we've got a few things going on here. Normal clocks, normal watches, they are going to operate with some sort of quartz crystal, and it's essentially resonating at a specific frequency that allows for it to maintain the movement of time, essentially. So it's moving the second hand because of its resonating frequency. You can think of a tuning fork when you hit it on something and then hold it to your ear. It's only going to ever ring at that frequency just based on the materials and the essentially the molecular makeup of the object. So we're doing the same thing with clocks. The problem with normal clocks and watches, as far as the quartz crystals go, they are sensitive to temperature and density humidity more specifically. So when you have those changes, it actually will speed up or slow down that resonant frequency ever so slightly. When we're talking about global positioning, we obviously want to shoot for the most accurate possible timekeeping device that we can get. Part of that is just the nature of the calculation. Another part is, as we are orbiting the Earth, we don't have an atmosphere, so that might seem like a good thing, but then as you get from the lighted side of the Earth to the dark side of the Earth, you have very large temperature swings. For anybody who has looked into anything with the International Space Station or even the space shuttle missions, that's usually a topic that gets covered. And so it's the exact same thing here. If normal quartz crystals are going to be thrown off a little bit by temperature, obviously we need to avoid that. And then lastly, we've got what we call time dilation, which jumps into a little bit of Einstein's theory of general relativity. So if anybody has seen the movie Interstellar, one of the first planets that they visit in the movie Interstellar is a planet that is very near a supermassive black hole. And if you remember, they have the landing party, they go to the surface, they think that they're there for only a couple hours. They go back to the ship that's orbiting in just above the planet, and that person is aged by, I think they said 7 years, but he has a beard. He's very frustrated. He's gone through all of his supplies. He's barely hanging on. And what's happened is when you are closer to a large body, the gravity is actually increased, and that actually will essentially slow time down. And it's not just the perception of time, but it's time itself. And that goes into what Einstein discovered about the relationship of space-time and ultimately gravity. So believe it or not, the satellites orbiting even in a near Earth orbit, that is a great enough distance that it is experiencing less gravity than we do on the surface. Therefore, the time in orbit is ever so slightly faster than the time on the surface. It doesn't make a big difference for our astronauts. They're not aging more, they're not aging by years more, I should say. But when you're talking about the accuracy that we need for clocks, that is going to be a difference, because if you're, going back to the quartz crystal watches, if you're deviating ever so slightly, those deviations are now amplified because of the difference in how time passes from orbit down to the surface of the Earth. All right, so skipping forward a little bit, what does that mean for our actual clocks on board the satellites? So the clocks are essentially a double redundant system. You have 2 rubidium and 2 cesium clocks. And essentially, these are 2 elements that their resonant frequency is so stable that there is virtually nothing that can change them. So we don't have to worry about the temperature differences. or any other environmental factors really. So as those base elements of rubidium and cesium are vibrating, the science itself gets pretty complex, but you can essentially distill it down to that resonant frequency is how they're basing the actual passage of time. So we're using two different elements to make sure that between using those two solutions, we get the same answer. And then, of course, we have two of each for simple redundancy. I think that's about all I want to cover there. I guess the one thing was they're not operating all four at once necessarily. As the ground control stations are evaluating the health of the satellite, they can essentially have the satellite use only two of the clocks and not the other two, so that it can essentially bring them down for maintenance, or if something breaks, then they still have the backup. So there's a lot of essentially automation or manipulation of the system even while they're in orbit, so that they can continue maintaining them without a human astronaut actually having to turn wrenches on the satellite itself, which I find pretty fascinating. All right, getting to the last piece of the puzzle here. So what we have is the actual navigation receiver, and it's going to come in all sorts of varieties. Just to show a couple examples here, just a very generic GPS unit that you would see on a boat. Obviously, you can get different overlays with nautical charts, which are going to be very helpful if you're coming in and out of a inlet or navigating sandbars. The one to the right of that is something that you'll see in more commercial applications. And similarly, its base function is to compute the position, but then we also have added features with aviation maps and kind of terrain and various performance in aircraft performance terms. This to the bottom left is actually what we use in the 65. It's a little bit of a older system, but it still works pretty darn well. So basically you're looking at one of two onboard computers. And as you can see, we've got our GPS position and then a few fancy GPS terms, a couple of which we will talk about briefly, and then all the way down to our smartphones. And so basically every single one of us has at least one, if not multiple GPS receivers in our hands every single day. And it's pretty impressive that the technology has gotten to this point, in my opinion, just that it's so readily available and so accurate. So just going through the bullets really quick. So as discussed before, we do have both military and civilian use, and it's the same system. One thing that I thought was interesting, and is actually partially, you might come across partially outdated information where it says that civilian models are less accurate, and that used to be extremely true in the sense that they used to intentionally essentially degrade the calculated positions and times of what the satellite was broadcasting to the civilian receivers. The idea was that, again, this is back in the 70s and 80s, we're still in very much a Cold War mentality. We don't want for just anybody to be able to use the GPS or to somehow infiltrate it. So if we intentionally degrade the signal to anybody who's not the US military, then we're somehow keeping the system overall safer. One of President Bill Clinton's last acts in office was actually to do away with that intentional degradation. There were quite a few reasons, part of it being the Cold War was over, but then a big portion of that reason was actually for purposes of search and rescue. The idea being that if somebody needs help and they do have some sort of GPS receiver, especially now with smartphones, we want to get the most accurate location on that person as quickly as possible, so that people like the Coast Guard can get out to them as quickly as possible and find them. So I thought that is interesting that that was done away with, and now everybody gets the exact same signal, therefore the exact same potential for the accurate solution. So the one difference that does still exist, things like this more simple version of the GPS receiver, and then certainly our phones, they're only going to have one receiver. So one receiver is pretty darn good. Although you may notice sometimes if you're driving on the highway, maybe your Google Maps or Apple Maps thinks that you've taken the exit when you haven't, or something similar. The reason for that is it only has one receiver, so it can only get so accurate. What the military does and like commercial aviation does, they will have multiple receivers, and essentially it's comparing the solution between the two receivers, and it's able to refine and figure out more accurately what the real solution is by comparing the two. And that's similar to what we do. I mentioned that in our helicopter, we actually have two of these computers. Both are running the entire time and comparing the solution. And so you can see this position index of 0.03 nautical miles. That's actually a little bit on the larger side for when this picture was taken. Normally we're, that position index is going to read within feet, but still pretty darn good. The essence of what the receiver is doing is solving for position, right? We know that. How does it do that? It is using the position broadcasted by each satellite with a timestamp of when that position was broadcasted. Since each satellite is going to be at a slightly different distance from the receiver, what the receiver is doing is solving a solution to compare what that time delay is. And through that time delay, it's able to solve for position. So if we just break this down very quickly, X, Y, and Z are going to be essentially your Cartesian coordinates. So I've drawn that out on the image of the globe here. So Z-axis along the north and south pole. X-axis is going to be the intersection of the prime meridian and the equator. And then Y-axis, of course, 90 degrees off of that. A, B, and C are going to be the position of the satellite. And so that's the position that's being broadcasted. And so you see here we have 1 through 4. So we're going to use at least 4 satellites in order to be able to solve this equation. Then you get into the end of the equation here, and the major factor is time. So if you've got a satellite at various positions, of course, they're going to have different positions that they're broadcasting, but ultimately it's using time and the time delay between each of those to figure out exactly where the receiver is located. Something that I think is kind of neat about this is you don't see anything in this equation that directly reflects where the surface of the Earth is. So what that means is automatically the equation solves for altitude. So it doesn't matter if you're on the surface, if you're flying, conceivably you could even be underwater or under the surface of the Earth. The only problem there, of course, is you're no longer receiving signals from a satellite. But in terms of altitude relative to the surface of the Earth, that is actually independent, which is kind of useful, at least in my profession, I guess you could say. The last thing that I wanted to touch on was the idea of the autonomous integrity of the system. So like we discussed with the equation, we need at least 4 satellites to be able to solve the equation. And again, you can think of the term triangulation, where we're using different points. Similar concepts are used if we are using just radar to determine position. We can use multiple radar sites, or if you are using line of bearing, where you're crossing the 2 different lines of bearing. So to relate it to other forms of navigation you may have learned, where they're still partly in use for nautical navigation. It's all very similar. Essentially, we're always using some form of time and speed to determine distance, or we're using some sort of comparison of time and speed to determine a position. So all the same ideas. The idea of the integrity monitoring, so RAIM, is if you have more than 4 satellites, you now have a 5th or even 6th or even 7th solution or comparison that you're able to use. And therefore, you're able to figure out if maybe one of the satellites is a little bit out of its orbit or something else is going on and it's not quite giving you a accurate solution. So if we have 5 satellites, we can say, okay, this solution might be a little bit off. If we have 6 satellites in view, we can say, okay, this solution is definitely off, and we know that this is the satellite that's not working properly. And in reality, we typically have anywhere between 7 and 12 satellites that are actually in view of any given receiver. So most of the time, our devices are automatically doing this. And it's very important because, as we were discussing earlier, we do periodically, or the Air Force, I should say, periodically has to conduct maintenance, or they realize that there is an error in some portion of the system, and we're going to have to correct for that. So that is the only way that we can figure out if we need that correction is by using the RAIM itself. And then just as the, to cover the last 2 bullets, if we have at least 24 satellites, which we pretty much always do, then we can use RAIM. If we don't have at least 24 satellites, there's actually different ways that we can introduce ground-based solutions, ground units to improve the solution and essentially get the same effect. All right. We'll get into some questions really quick. I do see we do have a couple Q&A bubbles at the top. Just to kind of get some gears turning about questions that you may have as we've been talking over this. These are 2 things that I started thinking about as I was researching the system. So first, I was considering, okay, if I've got 1,000 of my closest friends all in the same room, can we all get the same solution for where we're at in position of space? And the answer is 100% yes. So we are never using our receiver to send any signals to the satellite. It is only one-way communication going from the satellite to our receiver. So just like a radio, in terms of like an FM AM station that you may be listening to in the car, as many cars as can pile on that road, that's how many cars can receive that FM radio station. The exact same concept. So it's in a sense, it's a passive form of communication in the sense that we are only receiving the signal. There's no need to send a signal out. So no worries. We can put as many possible receivers in one spot and still get a solution. The other thing I was wondering was, does anybody else have their own system? And the answer is yes. Just to cover it briefly, Russia develops their global navigation system in a similar timeline that we did, again, going back to Cold War era. And those have largely been the 2 global navigation systems throughout time. The European Union mostly being funded and produced by Germany and Italy. They've developed their own system. It is also a global system, and all 3 of those are more or less similar in how they function. And then we have, of course, China, Japan, India are the other ones in that bullet. The 2 most notable things, they are more regional solutions. So they aren't as concerned with full global coverage. India's system is largely just based on providing position around India and its territories, similar for China and Japan. And they actually use slightly different methods to do that. And I thought this was kind of interesting. So India and actually Japan as well, they've got a 7 satellite based system. And It's not because it's a smaller region, because those satellites are still orbiting essentially most of the Earth. But what is different is, of those 7, 3 of those satellites are actually geostationary. So as we were talking about earlier, they're maintaining the same relative position above the surface of the Earth, while the other 4 are continuing their orbits. And it's essentially just a different technique of relaying those signals between the satellites and then ultimately to the user. And they're able to create a solution like that. So at this point, Josh, if you wouldn't mind coming back in to just help me get through the Q&A session, I would appreciate that.
Of course, Josh, and that will not get confusing at all. So
we can go back to calling me LT if that helps.
you're very nice, but yes, Lieutenant. So we have a person who asked 2 questions, and let's lump those together.
Okay.
And so the first part's a statement. You say that civilians get full access to the satellite's power.
Mhm.
And then the question is, I thought that satellites can read a dictionary lying on a parking lot. Why can't we see that power on Google Maps? And let's talk about security. Go for that.
Sure. Now I'm going to confess right now, I don't know as much about the actual satellite imaging. Ultimately, that is something else entirely. It's not related to GPS itself. So GPS satellites don't have cameras. They are just sending essentially radio signals. The imagery satellites, those are all military run, and they do operate on similar principles in terms of orbit, but they are completely separate from the GPS system. So ultimately, to answer that, I would have to do a whole bunch more research, and that would probably be a whole new tech talk. And I can't really say too much more than that, because otherwise I would be guessing.
Fair enough. So we have a question, and I'm not sure if they meant to say what instead of which, but the question begins with, which map datum and why example? Dash
Okay.
WGS 84, WGS 72.
So here, I'll share my screen again. I think that we're talking about my example in terms of where the air station was located. Is that correct? As near as we can guess.
Actually, I think what this is referencing, each GPS receiver can select which datum set it's referencing with the GPS signals. I know that the GPS receivers, both on my boat and the handheld one, give you an opportunity to select which datum. Every paper chart and electronic chart has inherent inaccuracies, and there are global standards that spec out how those inaccuracies are represented in the chart. And the receiver you can select which datum set the receiver is displaying.
Yes, thank you for covering that, Bruce. I appreciate you jumping in.
Thank you, Bruce. So have you heard of a private company trying to bring back Loran C?
I have not heard of that. I know that there are a few different discussions with the Elon Musk StarTech system and some of the capabilities it may be able to use and essentially enhance, but I don't believe that's based on Loran C. Loran C is heavily ground-based. It's very labor intensive. The Coast Guard had to have several stations located just about everywhere with 24/7 personnel on site to take care of the system. So Coast Guard has largely gone away from that. Well, they've entirely gone away from Loran C. They've largely gone away from anything that requires 24/7 personnel monitoring, because we have much better technology where we can do autonomous replications, essentially.
Yeah, that's a nice flashback to my youth with.
Yeah, I'm sure you could talk much more accurately about how Lurancy was used than I can.
It's been a long time. So we have a question here. Since the Earth is an oblate spheroid, does the system correct for tidal variations to determine a ship's actual location, since altitude would vary unlike ground or air positions?
Great question, and great knowledge of the Earth and how it's been. So what we're referring to partially is the Earth is not a perfect sphere. It is, since it's spinning, the equator is actually a slightly larger diameter than if you were to measure from pole to pole. And then in addition, as mentioned by the question, we have tidal variations. So what we talked about earlier when we were talking about the actual calculation of the solution is altitude is essentially automatically calculated because it's being calculated by the XYZ coordinate system. So the surface of the Earth is not in that equation at all. We are just calculating where it is from the origin or from the center of the Earth. And then in order to get a solution that you would actually have on a map, then we're going into, actually having a chart overlay and using that in essentially in the solution after the GPS position has been calculated. I think that answers the question. If it doesn't, we can certainly revisit it.
Yeah, he can shoot us a note. We'll deal with it in post, because that was really awesome. So do you need a different GPS receiver in Europe than you would use here in the US?
That's a great question. So if we are using the United States Air Force's GPS system, you would not need a different receiver. It would be the same receiver anywhere on the globe. And for a long time, that's actually what other countries did, or really more accurately, what other commercial enterprises did. So you can think of Garmin, or you can even think of Apple. They are essentially using the Air Force's system, and that's going to be the same anywhere in the world. One difference is now that the European Union, they actually just got a fully operational system this past year. So now that the European Union has their own system, obviously the device is going to be different because it's operating with a different set of satellites. And ultimately, that's going to just be based on whatever the company is selling as far as the product and how they design the system to work with whose ever satellites they're using.
Here's a satellite question. And do all countries that have GPS satellites maintain the same distance from Earth?
Well, if I understand the question, so the countries themselves, just being at different elevations, I guess the answer would be no, because this in a way goes back to what we were talking about with the altitude is calculated in reference from the center of the Earth. So once we get into the chart or the map that we want to represent that position on, now we're introducing the elevation. But say, here in New Jersey, our elevation is relatively zero or very close to it in terms of elevation above sea level, at least. Back home in Ohio, average elevation of Ohio is about 1,000 feet above sea level. So that's going to be different, but it's only represented by the chart itself. And that's going to be the same for any country. Once the solution is calculated, we just reference the chart and then they compare that.
So lightning round, so keep it yes, no, or short for the last minute.
Sorry, I tend to be long-winded.
No, complicated questions. Are there message formats other than NMEA?
I would have to revisit that. I don't know.
Okay. Your question. And some GPS denote positions as a single large number. How do we interpret that for latitude and longitude?
Excellent question. So I'll quickly go back to my screen on that as quickly as possible. So we briefly discuss that here in this slide. So this is essentially the format that you're talking about. And really, there's not a single straight answer. You're going to have to essentially do a little critical thinking. The one clue I can always give you is that in this solution, you see no decimal points anywhere in that number. So to me, that signals that they are reverting to the degrees, minutes, and seconds versus something like this, where it has a decimal point. You know that it's instead referencing a fraction. So that's the starting point. And hopefully they give you a couple more clues after that. But if there's no punctuation at all, I would probably say it's going to be this degrees, minutes, and seconds.
This is a flight question. Do we need ground receivers at airports to give a precision approach, or is this an old concept?
That's a great question. Both is the answer. So we have ground-based navigation, which still is in use. Most commonly, you can think of instrument landing system, and then we are transitioning to being more focused on the GPS solutions. And there are about 4 different levels of GPS accuracy when it comes to airport approaches. The most accurate is they include what's called WAS, and that is also using a ground-based station, but everything else with the GPS approaches is only using satellites. So it's only at that most accurate level that you have to have a ground-based source.
If you are getting your GPS positions over the radio, what's the best format?
Well, that's actually going to lead us into our practical exercise a little bit. So that must be a perfectly timed question. So the best format is whatever you're using for your device. If you can receive the position and then directly plug it into the radio, that's the one you want. If that's not what you're receiving, you're going to have to write it down and potentially do just a little bit of math to convert it.
Awesome. Last one on Zoom, then there's one on Facebook. My DSC VHF radio is connected to my Garmin chart plotter. I get 2 different latitude, longitude readouts. Is there something wrong with one or the other?
That sounds like more of a tech support question. That is a level of tech detail that I unfortunately don't know.
And that makes sense. Now, the one Facebook question, is there a challenge for navigation in the poles for GPS?
That's a great question. That is actually a big part of the 6 orbital planes that we have set up. So I'll keep this as brief as possible. It's actually not the poles that are the problem. It's actually the equator that's the problem. So the closer you get to the equator, the fewer satellites that you have in view. The closer you get to the poles, the more you have. The reason is none of the orbital planes are in line with the equator, but they all come close to the poles. So you have orbital planes that actually more overlap near the poles than they do near the equator.
Awesome. Well, that was the last question we had. Josh, I want to thank you for your time this evening. And everyone, thank you for tuning in. Bruce Johnson, thank you for your help. We'll be back next month for another webinar. And until then, everyone, stay safe and stay healthy. And if you can get on the water, go for it. So everyone, have a great evening. Thank you.
Thank you all.